In section 12.2, we introduce inverse kinematics. Here we'll demonstrate the geometric approach for 2 and 6 degree of freedom robots, and then an analytic approach for a 6 degree of freedom robot. So for the section 12.2, when we cover inverse kinematics, right now all we're going to try to do is get the mathematical response, is to get the solution. Just get a solution. We're not going to apply it to a robot yet. We're not going to use it in moving the robot yet. We're just going to say, if you have a pose, can you get a solution? If you have a pose, can you get a joint angle solution? That's all we're trying to do, and we're trying to understand a few of the details. Then in chapter 13, we're going to use solutions from inverse kinematics to start moving the arm to places that are important to us. Okay? So let's start by learning that actually for inverse kinematics, we have 3 ways of solving a problem. Number 1, you have a geometric solution or a geometric approach. That means you're using geometry, angles, the law of sines, the law of cosines. You're using the link lengths to try to find what would be the right angle, right? You have a position, and what you want is to get an angle. That's the geometric approach. The analytic approach is the second one, and that has to do with the way we compute forward kinematics. When we do forward kinematics, we have a transformation matrix, and that transformation matrix is really representing a system of equations. Yeah, it says x equals some combination of the joint angles of the robot, Q1, Q2, Q3, 4, 5, 6. Y equals some combination of the joint angles, Q1, Q2, Q3, Q6, something like that. So you get a for a 6 degree of freedom robot, you would have 6 equations: x, y, z, roll, pitch, yaw. Yeah, and then inverse kinematics. When you do the analytic approach, you're trying to solve for theta 1 from that set of equations. So you say, how can I isolate theta 1 and solve for it? How can I solve for theta 2 and isolate it? Yeah. So you have a system of equations that you're trying to solve in the analytic case. In the numeric case, the third one, you're using optimization. You're looking at where the endpoint is, where you want it to go, and you move the robot in a particular direction to try to minimize the error. So you might move it, you're trying to follow a gradient, and that gradient comes from the Jacobian. And so it's like, are you moving the right way, yes or no? And it's just trying many points until the error is smaller than some tolerance. So these are the 3 ways you can compute inverse kinematics. And many of these approaches, especially geometric and algebraic, will follow a robot-specific algorithm. So if you have you could have 2 robots that have 6 degrees of freedom, but actually the formation of their links is different. The placement of the links is different, or the frames of reference, I should say. The frames of reference placement is not the same. And so you would follow a different approach. Why? If you have at the wrist, if you have the 3 frames of reference for the last 3 joints, elite, right here. If the 3 frames of reference are on the same point, we call that a spherical joint. We'll see that a little bit later, and that makes computations of inverse kinematics easier. Spherical joint. If those 3 frames are at different locations, not at the same point, even though maybe you have the same number of joints, you would have a different derivation of the inverse kinematic solution. Okay, so it says, the idea is that it may be robot specific. Different solutions for different robots. And in inverse kinematics, we're going to see that often we're going to get multiple solutions. Multiple solutions. You don't have one answer. You could have 2, you could have 4, you could have 6, you could have 8, you could have an infinite number. And so in case of more than one solution, how do you choose? Sometimes you have 0 solutions as well. Okay? So basically in this chapter, we're going to start with a geometric approach using the law of cosines for a 2 degree of freedom robot. And then later we'll go to a 6 degree of freedom robot, show that a little bit. And finally, we're going to move to a 7 degree of freedom robot and switch to an analytic solution. And here you can see the files where the forward kinematics and the inverse kinematics are computed. So let's start with the 2 degree of freedom robot that we used for forward kinematics. You can see the image on the right. And here we have our 2 joints, right? One is the shoulder, represented by S or Q1 in this diagram. The other one is the elbow, represented by E or Q2. And then the end point of the robot can also be called the flange. Okay, the flange or the end point represented by F. So if we want to solve the inverse kinematics, what do we do? Well, here we're going to present the algorithm called IkSolve. This is a method found in the inverse kinematic library that I showed you, the file that I showed you before. And this method needs to take in as an input the pose, the x, y, z, and the RPY coordinate of the robot. Or in this case, I think it's just for the 2 degree of freedom case, we don't have the orientation, I'm sorry. So we just take the pose as a eigen of fin3 type. Okay? So eigen is, as you know, it's linear algebra library. And the affine type, affine 3 object here would take an XYZ point. And then you can also save here, sorry, I think it's not multiple poses, multiple joint configurations. Let me see, this is a vector 2. What did I write here? Sorry, I have a memory lapse here. Multiple poses are saved into a vector of type eigenvector 2. I don't remember clearly now what this is, but it sounds to me like it would be the solutions, but those would be, oh yeah. These are not poses. These are multiple joint angle solutions that can be saved in a vector of type eigenvector 2. What does that mean? Well, imagine that I'm trying to reach this particular point here. In this case, my elbow is down, but I could also reach that position like this with my elbow up. So in this case, you would have 2 joint angles for the shoulder and for the elbow, right? But you would get different solutions. One would be elbow down, the other one would be elbow up, right? So when you compute the inverse kinematics for one pose, you might have 2 solutions if you can reach that location. And so how do you output the result? You need a vector because you have more than one solution. And that vector is going to be eigenvector 2s because you have 2 joint angles for this particular problem, shoulder and elbow. Okay? So sorry, that's not multiple poses, that's multiple joint configurations. Now, for this 2 degree of freedom robot, we ask the question, what solutions are possible? And here, first, we need to know that the solutions only exist on a flat plane. If I only have a shoulder and an elbow, I can't rotate, right? So I might just be able to give you solutions on this plane, right? So that plane, in this slide, we're setting it like this would be at the plane that exists at y equals 0.2. Yeah? So you'd have to look into the environment to identify that plane, but that would be y equals 0.2. And so the thing that can vary then is the x direction and the z direction. And so at y equals 0.2, you have a combination of x's and z's that you can reach. Okay? And how do we, so this is a very brief example of how we might come up with a geometric solution. So if you look at this diagram and you look at both lengths, you could consider the law of cosines. The law of cosines has 3 sides, A, B, C, along with 3 angles, right? So in red letters over here, each of the lengths could represent one of the sides of a triangle, little a and little b. Little c is the distance between the flange and the shoulder. And that's the distance that you might care to set. What do you want that distance to be? As well as we would have 3 angles, but the angle that we care most about is Q2, which is the congruent angle with little c, which is big C, right? So the distance between, if we look at this equation, the distance between the shoulder and the flange is only a function of Q2, right? If we move Q1, we might move the rest of the arm up, we might move it down, but the distance between the endpoint and the shoulder is not affected by Q1. It's only affected by Q2. Yeah, so here we have the equation for law of cosine. C squared equals a squared plus b squared minus 2ab cosine of big C. A and b would be the linked lengths. C is the distance from the shoulder to the flange. And big C, the angle that we care about, would be Q2, right? So what you put in is the pose, x, here x, y, z, but what you want to get back is the joint angles. Now, I don't have the whole derivation here. We can go into the code to look at that later. Because right now, we're not trying to present the entire theory of inverse kinematics. We will do that in a manipulation class. But here, I'm just trying to give you enough information to be familiar with the approach and then see how we might do this in Ross. Okay? Again, if you want more information about inverse kinematics, for those of you who have not taken a manipulation class, you can refer to my class from last semester or Peter Kork's website or any other resource online, which I think is just you. Okay?
Awesome.
Oh, yeah, actually. So 2 of you are not very familiar with that. Now, I guess the first question is, when do we, for the law of cosines, mathematically, when do we not have a solution? Yeah, but so in this arm setup, we will, okay, when might we not have a triangle? There's a point at which that triangle disappears.
Yes.
When is that?
Yeah, cosine.
And what does that mean? What about the arm? The arm is straight. When the arm is straight, we still have a solution. Well, actually, we have an infinite number of solutions at that point. That's going to be a singularity. So, but when do we not have solutions?
First, if you cannot, the flange cannot reach the point.
Very good, Tony. So that means when C is greater than A plus B. So if you say, if your arm can only get to, say, 10, 0, 10, and you want it to go to 11, you can't do that. So there would be no solution for that, right? If you are asking it to reach a point within the workspace, then you can have multiple solutions like we discussed earlier. You can have the elbow up or the elbow down solution, which is represented here, okay? So what we're saying is that each elbow solution also has a corresponding shoulder angle. Yeah, this elbow angle has a corresponding shoulder angle, and this one too, right? Both the shoulder and the elbow happen. And when the arm is fully extended, not unique solution, infinite solutions. I'm sorry about that. Infinite solutions when the arm is extended. Why? Because this point can be reached here and here and here and here and here and here and here, right? All around the shoulder. Well, let me see. In this case, in the two, sorry, but that's assuming you have rotation here. We can just reach this with or maybe in the 2 degree of freedom it's a unique solution because it's just one angle here and one angle here. Yeah, that's for full extension and the 2 degree of freedom case. It is a unique solution because there's only one joint angle for the shoulder and the elbow that reach that location. But once we have the ability to rotate, then we have an infinite number of solutions there. Does that make sense? So if we want to find the corresponding shoulder angles for each elbow solution in our code, IK solve, and that method, we have another method called solve for shoulder angle. That method is using this law of sines. R equals A cosine of Q plus B sine of Q. And so from here, if you're solving, if you have an R and you're trying to get Q back, that's where you get two solutions. Okay, you're going to get two solutions from here. And that equation is solved inside this other method, solve K equations, A cosine plus B sine. Okay, and so it takes the parameters A and B. K would represent R here, I believe, and then it returns the Q solutions. And so you can get two solutions from here, shoulder, elbow up, elbow down solutions. Okay, so here if you just want to look at the solutions, we can run this code. Now we've done that last week. We've run this code last week as we were looking for forward kinematics. But today we're going to be focusing on the inverse kinematic solutions, okay? So let's try to run the RRBot, and we're going to use the test RBot FK. Start gazebo. It seems to me that when I connect the computer to the projector, it has a slower response. Because when I don't use the projector, it's so fast. I think the projector, something with the graphics slows it down. I reset everything today. I was thinking it's going to run fast, and it's still not fast. Are you guys trying to run it yourselves? No? Yeah?
Running.
Yeah, okay. Guys, for the inverse kinematics, sorry, it's the I wrote down this one as Ross Run, but it's also test planar 3R bot FKIK. Or maybe it is this one. Test R bot FK Ross Run.
This was wrong. R robot has to robot FK. Was wrong.
Was wrong or was right?
Was wrong.
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 It sounds like run. Wrong. So, sorry for that. So it's test planar R 3R robot FKIK. So the RRBot test FK, that's right. Yeah, it's test RRBot FK, that's right. Yep. So here we have that. So basically what we need to pay attention here is these two solutions, right? Now, how do these solutions come? It's saying that for the given pose that the robot has right now, yeah, what would be the joint angles of the robot? And now, which angles does the robot have right now? It must be one of these two. Yeah, it must be one of these two. So we could try to look at that in Ross topic list. Let's see, Ross topic list. We're looking at something like joint states, this one. Ross topic echo, clear the window, joint states. So we're looking at position. So here we have 1964 and negative 0.22. Yeah, so it's the second solution that we're using, right? So the question also is, how do we choose a solution? And we don't directly answer that question here today because a lot of it has to do with context. You need some idea of what you're trying to do to make a decision. Would this one make more sense? Would that one make more sense? If you don't have any preference at all, the most naive criteria would be choose the first one that you get. Or you could say choose a positive angle, choose elbow up because that's better for grabbing something instead of elbow down. things like that. So you need to have some kind of criteria to make those decisions. Okay. All right. And actually, if we were to move the joint angles, let's see how those solutions change. So I'm going to open RQT GUI. Which is very slow for me. You can try RQT GUI and then command different angles to the shoulder and to the elbow, and then look at how those solutions change. Actually, my RQT GUI just says updating, and it's not responding to the topics. Does your RQT GUI respond quickly?
Yes.
Yeah, it's something with the projector here, I think, that because it only happens in class. So you can command the arm to move to a different joint angle configuration and see the inverse kinematic solution updated. Are you running it, Ely? Yeah, change the arm position, move it to another place. I can do it from the command line. ROS topic pub 10 here. So I moved mine here on the command line, and then my solutions have changed as well. You can notice here the inverse sign, right? 0.0030 and then negative 0.0030, right? So just that elbow up and down, the shoulder is almost the same. Very small variation in the shoulder to get that response. Okay? All right. So let me kill all of that. I might even close the whole thing. And so here is just the slide that helps us to see what's going on when you move it to different locations. Yeah, do we have any questions? So, Eli, do you have any questions? He's trying. That's okay. So in the meantime, let me slowly then transition to the 6 degree of freedom case. We're going to look at this IRB 120, which is a ABB model. Yeah, ABB. And this robot has 6 degrees of freedom, right? One question that you want to quickly ask is, what about the wrist? What is the configuration of the wrist? The wrist is the end point of the robot, but what we're asking is, where are those frames located? And if you look at this diagram, we can see that this robot has a spherical joint. What does that mean? When we look at this endpoint, the frame at joint 4, the frame at joint 5, and the frame at joint 6 have the same origin. The blue axes here represent the z-axis of each of those frames. So you have maybe 4 like this, 5 like this, and then 6 like this. But they're all based at the same point. Yeah? So the distance from this joint, so this joint, is going to be the same for all 3 frames. But the orientation changes. Right? But when this happens, we say that this is a spherical joint. Why do we say it's a spherical joint? It's like a ball. And the human shoulder and the human wrist approximate a spherical joint. Because our wrist can go up and down, left and right, and have some kind of rotation. Right? Same as the shoulder. I can do this, and I can do this. Even though not exactly all of our joints are here, but the way our muscular skeleton system is composed, we have this ability. Mathematically, having this spherical wrist simplifies the computation of inverse kinematic equations. Okay? So that's important. Another thing that's going to happen is that when we have a solution, the wrist will be expressed in terms of the proximal joints. Proximal joints are going to be 1, 2, and 3. Yeah. So here too, we'll see in a second, we can have multiple solutions. And sometimes we'll see that maybe the wrist solution is the same, but the proximal joints are different. And other times we're going to see the proximal joints being the same and the wrist solution being different. For example, in this case, we have up to 8 solutions that are possible when we have a reachable point. What are those? As before, we have the elbow up and down solutions, okay? But then on top of that, because now we have the ability to rotate the wrist, we might have an elbow up, but with my wrist like this, or with my wrist rotated 180 degrees. I can't do it. The robot, depending on the robot configuration, this may be possible. Yeah? And you can also have an elbow down, with the wrist this way and the wrist this way. Here I can do it. Here it's a little bit easier here, but it's harder in these places, right? So these 2 combinations would give you 4 solutions, right? And then you also have the ability to rotate the base, and then do this. Elbow up, and then elbow down. And so that's another 2 combinations for a total of 8. So when you look at those solutions, for example, here you can see that these are the proximal joints right here, right? So here, these 2 proximal joints are the same. These didn't change, right? And then in these 2 cases, these didn't change. These didn't change, and these didn't change, right? So the things that change are going to be the last 3. So here the proximal joints are the same, but then this changes. So this might be a flipped wrist. And then here, this might be elbow up, and this might be elbow down. But here, the wrist changes. Yeah? So you can see like positive number, negative number here, positive, negative number here. And then these solutions repeat from up here, but now with the base rotated around. Yeah? Going from here to here. And so you get all those numbers there. Here you get the negative numbers of these, so the shoulder has to go back the other way. Yeah? So you get these negative numbers. These, I guess, stay the same, and then you still have those sets of combinations here. Does that make sense? So again, we can run it to see what the program gives us. So here we launch Gazebo, and then IRB 120 description, IRB 120 launch, and then IRB 120 FK IK test main. Okay, and you can move around. So please try. Yeah, you have it. So run the IR 120. Here, for example, you might try the value 1, 1, negative 1, 2, 1, 1. You might get this configuration. And so a few things to note on the terminal, because later you'll look at the code, so you want to be familiar with this. First of all, this code will give you what's the position of the flange, what's the position of the endpoint. So x 0.28, y 0.44, z 0.49. And when you look at that robot, you need to make, does that make sense? You would need to look at the base. You need to look at the direction of the reference frame. So x is probably this way, and then y is probably that way, and z is probably up, like that, right? So you expect a positive x direction. This might be a little bit rotated, so y is near 0, but not 0, and then z should be up, and depending on the size of the robot. So this is saying, hey, 28 centimeters forward. Here, well, this is not close to 0. I would have to see it from the top, but it says 44 centimeters to the side, and then 49 centimeters up. And that would be the position of, I think, this point right here, if I'm looking at that correctly. That's the flange or the endpoints, okay? And then this thing, what we currently have is this, as joint angles. Yeah, and because this is not moving, these joint angles should be the same as the solution. So here, these numbers are the same. Okay, that's the solution. This is the orientation of the robot in terms of a rotation matrix. It's a 3 by 3. Yeah, if you don't know how to think about this, you can think of this as a column vector that points towards the x direction, a column vector in the y direction, and a column vector in the z direction. If you could imagine that this is 1, and this is 1, and this is 1, so this would say the x direction is pointing, the x axis of the robot at the endpoint is pointing at 0, 1, 0. 0, 1, 0 would be that direction over there, remember? 0, 1, 0 is the y-axis. So maybe the endpoint is that one. It's kind of pointing towards the y-axis. Okay? And it's saying the y-axis is pointing to 1, 0, 0, which would be in the x direction. So imagine this is the x, something like this. Actually, this is kind of pointing in the y direction. So maybe it's like this. This is pointing in the y direction. So the y-axis might be pointing close to the x direction somehow, maybe the other way. And then the z direction is pointing 0, 0, negative 1. So actually it kind of looks like this is like this, like this. It kind of looks like this somehow. Yeah. That tells you the orientation. So you need to also be able to interpret this. Of course, I'm not moving this around. If I move it around, I think it'll be easier for me to see. But from this angle, it's a little bit tricky. And then it says number of IK solutions at this goal point, 8. And it gives them to you here, which are the same ones that I put on the slide. Okay? Here's 1, 1, 1, 1, and then these 4. So these don't change, these don't change. Flipping the wrist, elbow up, elbow down, like that, and then rotated laser. Right? This comment here, I don't know what it is. I haven't looked very precisely into the code, but we can do that.
How can we change the solution?
Change the solution in which way?
If we want to use another solution.
Out of those 8?
Yes. No, not out of those 8.
How do you choose one out of those 8?
In this 8 solution.
Within these 8, how do you choose one of them?
Yes.
Right? So that's a question we don't directly answer in the class, but it has to do with what do you want? So you might say, let's always choose base going forward as opposed to base rotating backwards. Because we're going to do a grab from the top, let's choose always elbow up. That gives you 2 solutions, the wrist like this or like this. And then you might arbitrarily say, let's choose the first one, or it doesn't matter, so choose any one of them. Or let's choose one that gives us more range of motion for a particular task. It's depending on those kinds of information. And you can of course build something more sophisticated that might do an optimization, says this one might be the best for this particular task. But in general, people are simply going to do very simple rules to choose their joint-out solution. Okay, so I'm going to stop this and go back. Just a representation here. So here, for example, you have your elbow up and your elbow down. Yeah, look at the colors of the axes. This is an RVIS. So the base is over here. RGB, X, Y, Z, X, Y, Z. Right? So if you do this, it's like that. And so nothing changes. And then we have elbow up and elbow down here. Elbow up, elbow down the same. But what's the difference here? Well, this is oh, this one. Well, let's see. This one is, I think, well, this is also. It's hard to see here, huh?
No, there's some difference.
There is a difference, but it's
这个是三的，像
hard to see
这个
here.
是三的，像确实不
I
同。
think these four is with the base rotated the other way. Hard to see. I don't know. I can't tell from looking at it. Okay, so now let's think about the space of solutions. When might there be less than 8 solutions? Of course, the first one is if the reach is beyond the limit of the robot. If you're asking it to go to a place it cannot reach, 0 solutions. If a pose is beyond the joint limit, less solutions. So remember that not all robot actuators rotate 360 degrees. They have limits. They might say, I can rotate from positive 180 to minus 180, or 90 to minus 90, or something, right? Just like our arm. That's all I can do, right? So maybe I can grab this here like this, but I cannot grab it like this. So I lose a solution there. Does that make sense? So if a pose is beyond a limit, you lose solutions. And if the robot is at a singular pose, infinite solutions. This is different from the 2 degree of freedom case. Okay, there in the singular solution for the 2 degree of freedom case, we just had one shoulder, one elbow. But here what we're going to have is infinite solutions. When 2 or more axes align, such that their joints are collinear, then there's an infinite solution. Imagine this is joint 4. And imagine this is joint 6, something like that. And then joint 5 moves me down like this. So now the z-axis of both of them is pointing in the same direction. So here you can reach this endpoint if you do this, right? I move this one to the right, I move this one to the left. Same for the robot is going to be the same thing. I move like this, it's the same thing. Yeah? So this is just infinite number of solutions when the 2 are aligned. Okay? That's a singularity. And in general, in code, we want to avoid singularities. Because they can cause problems. Sometimes we have singularities for the inverse kinematics here, but sometimes we have singularities with a straight arm for the Jacobian, and there's just different dangers that singularities pose in different circumstances. Normally we want to avoid them and plan for them. So maybe I'm moving like this, and I'm about to enter the straight arm situation, right? So there in your code, maybe you're measuring the Jacobian matrix, and you see that the determinant is moving closer to 0. And that means it's dangerous. So maybe you need to activate some technique for the robot to do something to avoid that. Yeah? Otherwise, if you enter that singularity, it may cause your system to crash. You might have a division by 0, infinite solutions, and if you don't plan for that, the robot might suddenly have very strange behavior. Okay? And then the other interesting case is if a robot has more than 6 degrees of freedom. What's funny? Something's funny? No. If we have more than 6 degrees of freedom, like 7 degrees of freedom in a robot arm, or potentially large numbers of degrees of freedom in flexible manipulators like snakes or elephant trunks, then you have redundancy. That redundancy means there's many ways to reach a solution. Here's a YouTube video that you can click on that link and then see an example of redundancy. But basically it's just like the human arm. If I grab a point here, I can still move my elbow and my shoulder in multiple configurations without changing that position. So the answer here is which one is the best of all these solutions? Some people might say, let's find the middle range, because you still can move like this and like this. For the human, most of the time is this one, which is less energy, so less work. Yeah, but again, you could have different criteria to say that. Some might say choose this one because maybe it's stronger. Your muscle is stronger at this position, maybe to push or something. Yeah, so you may have different criteria for that. In general, if the solution is reachable, you might have the same Q1, Q2, Q3, Q4, and you might still have those two wrist solutions to reach that point. But on top of that, that's in terms of Q5, Q6, Q7. You might have this and this. But then you still have Q1, Q2, Q3, Q4 back here. And that might have the continuum of solutions. Yeah? Or sometimes you can also say multiple limited or multiple discontinuous sets of solutions, because you might have this solution here, and if you do this, you might have this solution here. There are two separate continuums. Yeah, this one here, and then this one here. They're a little bit different, right? So you might have that. So you have some possibilities in the wrist, like this and like this, and for each of those, you also have a set of continuum solutions here and here for redundant manipulators. Does that make sense? So here I talk about the human arm. Now for this 7 degree of freedom, in this case we're using the analytical derivation. So we're working with this model for the 7 degree of freedom robot arm 7DOF. This is some kind of NASA arm or a simplification of the NASA arm. And so here we can use the FK-IK kinematics code. But in particular, so the question then would be, how do we choose the best solution? Here we're not answering that question yet, but we're going to have a few thoughts about it. In this case, we can also rotate the base behind and bring the shoulder up, right? And even because we have redundancy, I can do this. Let's say I'm grabbing here. I can do this, and I can do this. If you think about the base of the robot can rotate to some degree, and those joints can kind of move like this to get a solution at that point. Yeah, it might look like this, or it might look like this. You have all that space to do it. And this would be elbow down, and the robot might still be able to do an elbow up for that. So this code, what it's doing, it's saying, hey, let's get the IK wrist solutions for a fixed Q0. Actually, I need to clarify something here. When we talk about C++ code, all of our arrays start at index 0, right? So you would have 0, 1, 2, 3, 4, 5, 6. So here the code, when it says Q0, it's referring to C++ code. When we talk about DH parameters, there's no 0 joint. It starts from 1. So in the text, the base is described as a Q1 input. So you've got to make the distinction between the code and just the regular description or presentation of the inverse kinematics. Okay? You've got to be careful about that. So here, this method, what it's doing, it says, give me a post, but also give me a desired Q1. Now, maybe here. And what this ends up doing, you might have 4 potential solutions for these angles, because you fixed the Q1. So Q2, 3, and 4 might give you different solutions. 4, and then at the wrist, at the endpoint, you might have those flipping solutions, 5, 6, and 7. Okay? But if you say, give me a desired Q1 angle, how do you choose Q1 is still unclear, because you still have that range here. So what this algorithm is also doing is a few things. It says, we need more context to decide, but let's compute a range of inverse kinematic solutions for a range of Q1s. So it's going to be like, let's find the IK solution here, and here, and here, and here, and here, and then here, 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 and here. Something like that. In fact, so inside of this one, you have IK solutions, sample the Q's, the angle 0. What it does is you give it a pose and it returns a vector of IK solutions, and it needs a resolution of Q1 angles. Resolution here means how often should I check the Q1 angle solution? So if the resolution is 1 degree, you might say when Q1 is 0, when Q1 is 1, when Q1 is 2, when Q1 is 3. We're looking at radians, right? So a complete circle is 2 pi. Right? You might say, let's make the base angle, let's call it Q1, 0.1 radians. So I might check here, 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 here. And here the range is going to go from 0 to 2 pi. Of course, if the goal is here, the robot will have a limit on both sides. I can reach here and I can reach here. Outside of this point, there's no solution. This algorithm, though, is checking that Q1 around the whole circle at a particular resolution. So it might say, I can give you IK solutions from here to here, and then here I cannot give to you. Does that make sense? Let me draw it on the board. Maybe I should include a diagram. We're trying to go here, and we're here. And the arm maybe can have this configuration, can have this configuration. Let me see. How can I draw that? It's hard to draw because it's 7 degrees of freedom, but basically it can kind of do something like this, right? But there will be a limit as to maybe out here it cannot do it anymore, and out here it cannot do it anymore. So I might say I'm going to return solutions to you from here to here. But anyways, we're still going to check around 2 pi. The closer it is, the wider you can go. Right? So it's like if the arm is straight, maybe you can just do this. But as you come closer and closer, right, this angle keeps growing. Almost, if it's close to you, this is almost flat. And then you could have so many ways of getting to that. Let's, I didn't write down how to run this. Why did I not write down how to run this? But let's try to run it. Okay. This is package ARM 7 degrees of freedom. So we start with model. Yeah, and here, launch. We're going to do with position controller. ROS launch, this one. This one needs gazebo, so ROS launch, gazebo ROS, empty world. Guys, how did I find it? Because I couldn't remember where it was. This is the first thing that I did. I said ROS CD ARM 7. Yeah, 7.dov. I double tab on that, and I know it's model. So I ROS CD into that. Then I do a list. I know it's inside the launch file, so I just say CD launch. Yeah, so we're in ARM 7.dov model launch. Then I do a listing, and I look at the position controller. Once you're inside the folder like this, you can just say ROS launch, copy, and paste. You don't need to put the package name if you're in the same folder. The package name is a path, but if you're there, you can then just run it directly. Okay. And then we need to start gazebo first. Sometimes I don't remember if they need gazebo or don't need gazebo. Sometimes it varies. So start gazebo and then start the position controller. In gazebo, you can always close this window to give you a little bit more space, and then put that on the side, run this one. So this is going to spawn the model into gazebo and then start the position controllers. When it comes to the kinematics, again, you can say raw CD arm 7. Double tap on that, and you can see here you have the FKIK package, so you can go into that. So you're in the FKIK package. You can list and see what the code is. You can go into source, and so you can see that you have 3 different possibilities here. I guess I'm missing a slide because I haven't told you which programs to run. This main 2 is the program that looks for a range of angles at the base to find IK solutions. So here you could say Rust run arm 7 DOF FKIK main 2. And this is actually going to run very quickly. Let me minimize that. It's publishing a lot of stuff. It looks a little bit confusing. I'll show you what it is in a second. Okay, let me stop it. So if we go to the top, it starts here. It kind of starts here. It says number of solutions found 0 at negative, at 2, maybe here. Number of solutions found equals 0 at negative 3. So negative 3 is moving 180 degrees back, almost 180 degrees back, and says, I cannot reach that point if my arm is over here. And then it goes to negative 2.9, 2.8, right? And it says, I cannot do it because this desired is out of reach at full elbow extension. So you get some warnings, and then when you get to negative 0.1, it says number of solutions found, still 0 here, but then 7 at this angle, so almost at 0. And then 7, 6, 7, 7, 8, 8, 8, 8, 8, 8, 8, 8, 7, 6, 6, 7, 8, 8, 8 here. So you get a range from 0 to 1.8 for that base angle, from here to 1.8, which is more than 90 degrees, to about here. That arm can find solutions, even up to 8, for that point. Okay? And then it says, I can't find anything else after that. This code is currently using what kind of inverse kinematic approach? Geometric, analytic, or numeric? Analytic. This is analytic. So the easy cases for 2 degrees and 6 degrees, we use geometric. This is using analytic. Okay? And so there's a few things I want to tell you about analytic stuff. So analytic versus numeric computations. Numerical algorithms follow gradient descent. That gradient descent has to do with error or slopes, right? Gradient descent of the error of the manipulator Jacobian. And it needs to converge. So maybe your arm is here and the goal is here. It's going to like test the space. Which one is closer to the goal? Say, oh, this is closer to the goal, right? And converge means it needs to be smaller than some error. Can your endpoint reach a location with a very small error? Yes or no? That's convergence. Sometimes the algorithm may have problems and may not converge for different reasons. Sometimes numeric algorithms start with a guess. You might say, this is my current position, but you might need to go over here with some strange pose. And might start doing this, and it's like, okay, but it might be too slow, it might time out. Or it might have gone the wrong way and it didn't find it. It got stuck in a local minima or something like that. In a position that it thought it was good, but actually it wasn't good. Because it's a little bit blind, it's just kind of following what it thinks is right, but it may not get there. Okay, but let's see, analytic solution has strengths. For example, you don't run the risk of non-convergence. Analytic means you have an equation, so it kind of looks like theta 1 equals some ax, some by, some cz, something else for the rotation, okay, some d for the roll, and like that. So it's an equation, right? And once you have x, and once you have y, and once you have z, you solve your equation very fast. You just run it, compute it very fast. And so you don't run the risk of non-convergence. In the example that we just ran, basically we can find, if you read the book, 220 solutions in total. But how long do you think it takes to find 220 solutions? Guess. Well, actually, that is a very silly question in some sense because it depends on the processor, right?
Yeah.
But it says if you have an i7 and you just use one CPU, it takes 30 milliseconds. Yeah. So it's 0.0, yeah, 0.03 seconds, or 30 milliseconds, to find 220 solutions. So in 1 second you can find thousands and thousands of solutions. That's very good, that's fast. Okay? So you don't have to spend a lot of time thinking. If you need to move the arm to many places, every time you move you can find many solutions very quickly. There's an algorithm, a package called IKFast. And what IKFast does, it finds analytic solutions for a robot. Yeah, if you click on this link, it'll take you to a page from a guy called Rosen Diakonov. He was a student at CMU. He runs a company in Japan now for pick and place of industrial things. He created IKFast. And so IKFast is nice because it can find automatically the analytic solution for different robot types. You set it up, you run the algorithm, and it'll find the numeric solution. Sometimes it cannot, sometimes, most of the time it will. Okay? It's a little bit hard to set up. There's a lot of things you need to learn in running this code. But if you can do it, it'll run very fast, and it would be the best way to do it. Analytic solutions, if you can find them, use them, because they're faster. But sometimes you cannot find analytic solutions. The model of the robot is so complicated that it's just too hard for us to find them, at least at this stage. So when we cannot find them, an alternative is numerical solutions. And so the strength of this is it can resolve hard to find solutions, but it needs a guess. And so here I just say, you can use the current pose wherever you are, that's your guess to start. Or sometimes what you can do, let's say, let me explain this to you. Let's say I have a 7 degree of freedom arm and it's too hard to find the exact analytic solution for that robot. Okay, too hard, you cannot do it. But let's say you make some assumptions and you simplify your robot model. Then you can find an analytic solution. But because you simplified the robot model, the analytic solution is wrong. So maybe when you use that model, and you want to go here, the joint angles that it returns to you might be with the robot being not here, but here. And then you can use that guess for the numerical algorithm. You have two. You have an approximate analytic solution. approximate. That gives you the wrong angles, but it gives you angles that are very close to the answer. You use those angles as the initial starting position for this one. And then this one can find the final solution. Because remember, for the numerical algorithm, you need to give a starting position. You want to go here. And maybe you give the starting point, so it needs to find the solution like this, right? But if you use the approximate analytic solution, it might give you angles that are here. It's closer than here. So then it just does this. So you quickly get this one and then converge here, which is faster than starting here and trying to figure this out. Does that make sense? So that's a better, even better way to combine approximate analytic with numerical. Okay, for something that I talked with Wyatt, the guy who wrote the book, he didn't talk about IK-FAST and track IK, okay? For the next 30 minutes, I want you guys to try track IK, but let me give you a few pointers. Track IK, so we have track IK, we have KPL, and we have IK-FAST as packages in ROS. Also, in this book, we have derivations of analytic solutions for UR10, Baxter, the R bots, and the NASA robot arm. Those are inverse analytic solutions that his group derived over time. Okay? So you can use those inverse kinematics for Baxter, or we can maybe change them for UR10. The UR10 and the UR5 are the same, except for maybe a few differences in the link lengths, something like that. The motors are stronger, but the kinematics will be derived the same way. We could always use that code for inverse kinematics, but you can also use this code for inverse kinematics as well. These two use numeric solutions, but this one is more accurate and faster than this one. Yeah? So I want you to study this one for now. IK-FAST is not numeric, it's analytic, and can be used with MoveIt, and can be used with ROS in general. I don't want you to study that right now, but you can study that later if you're interested. Okay, IK-FAST. So what I want you to do right now is spend 30 minutes looking at track IK, but let me give you some pointers, okay? You can also study this code that we looked at in class for later time. So all of you should have by default track IK in your computer. And there's a particular folder called track IK examples. Okay? So if you go to track IK examples, you'll see this launch file. Okay? Now for you guys, you'll just see pr2arm.launch. Let me show it to you. First, we're going to have some arguments. These arguments are for the track IK algorithm. Number of samples. It's the number of, let me see.
The trials, how many points for this rate?
Yeah, it's between the start position and the goal position.
Yeah.
How many inverse kinematics points should you have?
Mm-hmm.
Then it needs two names: the start of the chain, or the starting frame, and the ending frame. So for the PR2, torso lift link and right wrist row link. For Baxter, we're going to use base and right gripper, or right finger. I'll check in a second. And then you have a timeout, like how much time do you have to compute something. Then in this case, it's loading the robot description. For us, what we're going to do is we're going to launch one of our own simulated examples for Baxter. And when you do that, actually we can just do the regular Baxter for now. The robot description parameter will be in the server, and we can just use that. But this says we need to have robot description on the parameter server in order to run TrackIK. And then we're going to have this TrackIK examples package, and we're going to run first IK tests. And IK tests is a node designed to compare the performance of KDL with TrackIK.
Yeah.
And so you're going to get two pieces of information. How many solutions can TrackIK find? How many solutions can KDL find? You'll see that TrackIK finds more. Sorry, how does it work? You have, what it's going to do, it's going to load the URDF. And from the URDF, the algorithm will know the upper limits and the lower limits of all joint angles. It'll say, oh, this shoulder can move like this, and like this, and like this. Those are my limits there. And the elbow can do this. Those are the limits. And the wrist can do this, 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 and this. And it'll use a random generator to choose joint values within all the limits. It'll say, okay, this one, this one, this one, this one. Okay, I can reach that. It'll get that point and try to compute the inverse kinematics. Okay? That's how it's, and then it'll say, oh, let me try this point. I can reach that one. Let me find the inverse kinematics. This one, let me find the inverse kinematics. So it just does random poses the whole time. And it says, can I find the inverse kinematics? Yeah? It finds a random value and then just computes the inverse kinematics. It's not moving the robot. Right now it's not moving the robot. It gets the limits, randomly chooses inside the limits, computes the inverse kinematics. Can I do it? Yes or no? Okay? So what I want you to do, oh, and by the way, so this, you should be familiar with this launch file. Sorry. You should be familiar with this launch file. Let me close that again to make it look nice. With this format, what is this doing? You have a node, and inside that node, you have certain parameters. These parameters are going to be read by the C++ code or the Python code, number of samples, chain start, chain end, and these values are assigned in this way by these guys over here, right? I hope you feel familiar with that. So what you need to do is make this work for Baxter. But there's going to be two steps. Two steps I want you to try to do. Number one, first just change the code to work with Baxter. And then the second part, once you get that working, is after you get the IK solution, then move Baxter there. Move Baxter there. So you're going to get an IK solution, right? You're going to say join angles and then move. Okay? For you, you may not be familiar with Baxter, right? You are not, right? But everyone else should be, right? Everyone else is familiar with Baxter. So for the new guys, you need a little bit extra work to do. Let me show you. Actually, it's not too hard to get started, but you go to SDK rethinkrobotics.com, and this website will have the tutorial for you to get started. Okay? I've also, after this class, I will send you a PPT that teaches you everything about Baxter. Okay? I won't teach it in class. I should teach it in class, but we're out of time. So I'm just going to send you, for you guys, the PPT about Baxter, which a lot of it is kind of emphasizing things from the website and how to control Baxter in simulation. And the real robot is the same as the simulation. Okay, so a little bit more clue. Let me show you. As you can open I create a Baxter launch file. I changed these names. Actually, I found, you can try different ways. You may not need this command if you first launch Baxter. If you first launch Baxter, because actually I didn't finish this to show you guys exactly. So for the new guys, once you install Baxter, you can start by saying, let's start the simulator environment, baxter.shsim. It'll set up the terminal to run Baxter. You can say Rust launch, Baxter Gazebo, Baxter world.launch. Or let me see, is it Baxter world, should be world. So slow. So Baxter world. Yeah. My computer is super fast, but here you can see how slow it is. Still waiting. So you do that, and it's going to open the Baxter Gazebo simulation. And if we do the ROS param list in a second, we'll see the robot description up there, I think. So after the robot begins to start, you see robot description there, right? So then you have Baxter's URDF on the parameter server. So if you go back over here, you don't really need to. You don't need this. You don't need this line here. You don't need that line there. Okay, you don't need that. You just need this and this, because the URDF is going to be uploaded by the Gazebo launcher. Okay, so then you can do this. But what I want you to do is, of course, look at the CPP code. Look at the CPP code. So here, you would go to the source folder, and here you have IK tests. Okay, so you open that. And you'll start to see, basically test is the most important part. Now let me give you a little bit of advice. So you have something like this. What is this? Here you're creating an object, TrackIK solver object, which is of type TrackIK, and needs the beginning of the chain, the end of the chain, the URDF, a timeout, and a EPS. That's a little error thing, which is here. Once you do that, you can use this object to compute the inverse kinematic solutions. The first thing that you need to do is get the chain, the kinematic chain, the transformations from the URDF. That's a forward kinematics problem. So to do that, we can use KDL. We're going to do KDL chain, create an object called chain. We're also going to get lower limits and upper limits. These are joint angles, right? If you have 6 degrees of freedom, how many lower limits are you going to get? 6. And 6 upper limits, right? 1 for each joint. That can be a KDL joint array. That means it's like a vector of 6 numbers. Yeah? For the 6th degree of freedom. Baxter is a 7 degree of freedom robot, so this would be 7 numbers. Then you use this object that you created here and you say get the KDL chain. And then you save the answer here. So this chain is the kinematic chain, and you're going to use that for solving inverse kinematics. Here you can say, use this function get KDL limits and pass these two joint arrays LL and UL and solve them. The track solver here has access to this chain, so it can also compute this and return the valid response. Assert here is return true if this is equal to that. Else, get out of the program. Okay, that's what assert does. You can look it up. And so here you just report, I'm using 7 joints. Okay, now we're going to get a forward kinematic solver. Here you're using a pseudo inverse for velocity, and let's see, and let me see, let me remember. So how do we create the forward kinematic solver? You're going to use KDL, and you say chain forward kinematic solver precision recursive. Now this is a little bit deeper. You need to understand the KDL API, which you don't. But for now, it's enough for you to know, okay, I'm going to use this for forward kinematics. It needs the chain, so you give that to it. This is going to be kind of like a velocity inverse kinematic solver. It also needs the chain. And then this is KDL solver. You need chain, lower limits, upper limits, FK solver, VIK solver. Not sure what the one is here, and some tolerance error. Now this is for KDL, not track IK. Okay, but this is going to help you compute inverse kinematics, and then we're going to compare to that track IK. Then what we want to do is create a position for the robot that is in the middle of all the joint ranges. So if I can go from here to here, give me the angle that is in the middle. If I can go from here to here, give me the angle that is in the middle. Yeah, so this thing, when we say, first, it's going to be called nominal. Number one, get the number of joints to give it the size. And then we're going to fill it with, get the lower limit plus the upper limit divided by 2. Right, and so that's going to be nominal. Okay, so that's where maybe we're going to start. The next thing we do is create a desired number of valid but random joint configurations. So that's like, here we're going to create random configurations here, 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 here. I can reach all those places, but they're random. How do we do that? The number of samples determines how many configurations I'm going to create. And you say, for each of the joints, J0 to the size of this joint array, which is going to be 7, take this function frand, and for each j, return some number between the lower limit and the upper limit. Okay? That's qj. So you're going to do this 7 times. You get a random joint configuration. And then you take that q and you push it back on joint list that we created up there. Yeah. Another thing that we're going to do is measure the time. So here, Boost is a library that has many useful functions. You're going to use something called POSIX time that can measure time very quickly, and then use this object ptime, POSIX time, and you're going to call it start time. And then you're going to have another one that measures the time duration, which is going to be called difference. Okay, let's see how it's used. Here we're going to compute inverse kinematics, but also going to measure the time. So for the number of samples, take the forward kinematic solver and convert from joint angles to Cartesian. That's forward kinematics, right? Give the joint list indexed by I. That joint list we filled up earlier, right? 1,000 random configurations. And the end effector pose. That's going to be the output. Right now we have the angles, and what we want is the end effector pose. That's going to be the output of the forward kinematics. Here, we're going to start measuring the time, set the elapsed time to 0, take the nominal configuration of the robot, set it to result. Here we're going to say start time. So you say boost, POSIX, time, microseconds clock, local time. That's going to be my start time. Okay, we created this above, but here we're going to give it the value of the local time. We take result, copy it over to Q, and then say, let's do the KDL solver, inverse kinematics, Cartesian to joints. Okay, so here's the end effector pose that we got from here. And this is, because this is using numerical analysis, we need a guess, right? Right? We need a place to start. That place to start is going to be this one, I believe. No, it's going to be Q. That's the place to start, and it's going to give the result here. Okay? The final answer. The inverse kinematics are going to be the joint angles. And here you find the difference in time. Local time minus start time is difference. And then for this elapsed time, you need to divide by 1e to the 9, because this is a type for very fast time, for very short periods. So it's in these units, and so to get normal seconds, you need to divide by this. So this will give you the time, and you're going to do this for as long as you can for all the number of samples. And then here it's going to give you the percentage of successes and time. And then here we're going to do testing track IK. And really these are the methods that you need to be familiar with, really most specifically this one. Track IK solver, card to joint. This is your guess. This is where you are currently, and this is the result. So this is all you need to do the inverse kinematics with track IK. Okay? You have a start position, you have your pose, you have a joint angle start position, you have your pose. Here the start position is the nominal, right? If you're doing a real experiment, you won't give the nominal, you would just give wherever you are. And if you have a better solution like the approximate analytic solution, you could use that. Yeah, but let's say you're here and your nominal pose is here, there's no sense in giving this one if you're going to go from here to here, something like that. Yep. So, but really this is all, that's the main line, okay? The other stuff is just setting up. And so I want you to spend 30 minutes to look at this code, adapt it to Baxter. First, you just load Baxter in Gazebo, get the URDF from there, run this code. Maybe you can debug it or just run it directly if it works. And then if you can, once you get this result, which is still in joint limits notation, you'll need to copy that into a ROS message and then publish it to the joint command topic. Yeah, this is the answer, right? Result is the answer. Now, give it to Baxter. How do we do that? Copy each element from this joint vector to Baxter, what is it? Baxter messages, joint command. Angle 1, copy. Angle 2, copy. Angle 3, copy. And then send it to the publishing topic. Okay? All right, go ahead. 30 minutes.